Swayam Prabha. Digital India. Educated India.
So, till now what we have covered is that we have started with the transform techniques, that is Laplace transform, Fourier transform, their solutions using the ordinary differential equation, partial differential equation, the properties of various transforms, and after that we have done the finite Fourier sine and cosine transform. Now, let us come to the two more different transforms. The first one is Mellin transform. This particular transform is also used in various applications in real life problems of physics, electrical and electronics. So, just see what are these transform, how they are being used. So, in the Mellin transform, what happens? First let us go to the definition of Mellin transform. Let f x be a real valued function defined over 0 to infinity and s be a complex number. Then the Mellin transform of f x is defined as, which we are denoting as m of f x, which we are telling that capital F bar s, which denotes that the Mellin transform of the function f x, which is equals 0 to infinity x to the power s minus 1 into f x dx, where as I have written already s be the complex number. So, basically for Mellin transform, the kernel is x to the power s minus 1. So, whenever I am changing the kernel, then I am getting the other transform. Similarly, the inverse Mellin transform of f x is defined as m inverse f bar s, which is equals f x, and if you see, this is equals 1 by twice pi I c minus I infinity to c plus I infinity f bar s x bar x to the power minus s ds, where c is greater than 0. Due to the problem of the number of lectures, I am not going to the details that how we have got this particular definition. Directly I will use the definition, this definition, and I will use certain, we will see how to find out the Mellin transform of different functions and what are the properties of this Mellin transform. So, as again I am saying, the Mellin transform of f x, which we can denote as m of f x, this is equals to f bar s, this is equals 0 to infinity x to the power s minus 1 into f x dx. So, this is equation 1. So, as I told you, your kernel here is x to the power s minus 1. For Laplace transform it was different, for Fourier transform it was different, for Fourier sine and cosine also it was different. So, whenever I am changing the kernel, then I am getting various kind of transforms, and please note that here s is the complex number. Similarly, the inverse of Mellin transform I can obtain as m inverse f bar s. This is equals nothing but you will obtain the function f x. This equals 1 by twice pi I into c minus I infinity to c plus I infinity, c minus I infinity to c plus I infinity f bar s and x to the power minus s into ds, where your c is greater than 0. So, this is the definition of Mellin transform and the inverse Mellin transform, and using these definitions we will see how to find out the Mellin transform of some functions and what are the properties available over there. So, this already I have told. Now, let us see one example, Mellin transform of some well known functions. The first one is f x equals e to the power minus a x, where a is greater than 0. So, your function is f x equals e to the power minus a x, where it is told that a greater than 0. Mellin transform of e to the power minus a x. From definition, you can write down 0 to infinity x to the power s minus 1 into e power minus a x into dx. On this, if you put a x equals b, say, I am substituting a x equals b, so that this will be equals to x to the power x is equals to, here it is v by a. So, x to the power s minus 1 means 1 by a to the power s minus 1, and whenever I will differentiate it, dx will be 1 by a dv. So, it will become 1 by a to the power s 0 to infinity v to the power s minus 1 into e power minus v dv. And if you see 0 to infinity v to the power s minus 1 e to the power minus b, this particular integral is well known and its value is nothing but gamma s. I am not going again. This, if I evaluate the integral 0 to infinity b to the power s minus 1 e power minus b dv, then I will obtain gamma s. So, that I will obtain the result as gamma s by a to the power s. Therefore, the Mellin transform of e power minus a x is equals to gamma s by a to the power s. Just see this one. Your function is given like this, f x equals e to the power minus a x. So, whenever I am taking the Mellin transform from definition, as we know 0 to infinity x to the power s minus 1 into f x dx. Here your f x is e to the power minus a x. So, that I will obtain 0 to infinity x to the power s minus 1 e power minus a x dx. So, that put a x equals v, then this integral will be transformed to 1 by a to the power s 0 to infinity v to the power s minus 1 into e power minus v dv. And this integral 0 to infinity v to the power s minus 1 e power minus v dv is nothing but gamma s. So, that the result is gamma s by a to the power s. Therefore, Mellin transform of e power minus a x is equals to gamma s by a to the power s. The second one, if we take f x equals 1 by 1 plus x. So, your second problem is f x equals 1 by 1 plus x. So, Mellin transform of this f x, that is 1 by 1 plus x. From definition, you can write down 0 to infinity x to the power s minus 1 into 1 by 1 plus x dx. Now, if I substitute, say x equals v minus 1 minus v, x equals v by 1 minus v. So, that if you calculate v, this will become x by 1 plus x. From here, if you calculate v, b will become x by 1 plus x. So, that your 1 minus v, this will be 1 minus x by 1 plus x, 1 minus v is 1 minus this, and if you calculate this 1 plus x minus x. So, 1 minus v is becoming 1 plus x. So, if I put it here, you see your v is x by 1 plus x and x is v by 1 minus v. So, that whenever x is 0, your v is equals to 0. And from here, whenever you put x equals infinity, the limit over here it becomes 0 to 1, because your value of v will be 1, because x by 1 plus x I can write down 1 by 1 plus x plus 1, and so this becomes 1. So, as x approaches infinity, v approaches 1, and as x approaches 0, v approaches 0. So, the limit will be from 0 to 1, x means v to the power s minus 1 divided by 1 minus v. So, 1 minus v to the power s minus 1 into 1 plus 1 by 1 plus x is nothing but 1 minus v into your dv by 1 minus v whole square. So, once I am getting this equals, you can write down 0 to 1 v to the power s minus 1 into, I can write it as, here 1 minus v is there. So, this I can write down 1 minus v to the power 1 minus s minus 1, because it is actually becoming, one denominator becomes 1 minus v to the power s. You had 1 minus v in the numerator and here 1 minus v whole square. So, 1 minus v will be cancelled, only 1 minus v will be there. So, you have 1 minus v to the power s minus 1, s only will be there, this plus 1 will be cancelled, and 1 minus v to the power s, if I go up it will be minus s. So, I am writing 1 minus v to the power 1 minus s minus 1 into dv. Again, this is a well known function. Value of this integral 0 to 1, basically it is of the form that x to the power s minus 1 into 1 minus x to the power n minus m minus 1. So, this value is nothing but, this is a beta function, beta s comma 1 minus s. The value of this given integral, again it is known to us, this will be equals to beta s comma 1 minus s, and this equals, I can write down gamma s into gamma 1 minus s, whose results are known again to us. So, therefore, the Mellin function of 1 by 1 plus x, this is equals to beta s 1 minus x, and this equals, you can write down gamma s into gamma 1 minus s. So, if I see the problem over here, your f x is 1 by 1 plus x. If I take Mellin function 0 to infinity x to the power s minus 1, 1 by 1 plus x dx, which is nothing but, if I put x equals v by 1 minus v, I have shown the calculation in details. So, this becomes this integral, and this I can write it as 0 to 1 v to the power s minus 1 into 1 minus v to the power minus s actually, and minus s can be written as 1 minus s minus 1 into dv. And this function is nothing but beta mn type of function, which is the beta s beta 1 minus s, and this equals, you can write down gamma s into gamma 1 minus x. So, that the Mellin function of 1 by 1 plus x equals gamma s into gamma 1 minus s. Next, see the function f x equals e power x minus 1 whole to the power minus 1, or 1 by e power x minus 1. Let us see, your f x we have written as e power x minus 1 whole to the power minus 1. So, that Mellin function of 1 by e to the power x minus 1, this is equals 0 to infinity from the definition x to the power s minus 1 into 1 by e to the power x minus 1 dx. Now, I know that summation n equals 0 to infinity e power minus n x, this is equals 1 by 1 minus e power minus x. Therefore, summation n equals, I can write down summation n equals 1 to infinity e power minus n x, this will be equals to 1 by e power x minus 1. From this I can write down this. So, I am using this property that summation n equals 1 to n equals 0 to infinity e power minus n x equals 1 by 1 minus e power minus x, and from here I can write down summation n equals 1 to infinity e power minus n x. This is equals 1 by e power minus x into 1. So, that 1 by e power minus x into 1 in this given integral, I can simply replace this value by this summation n equals 1 to infinity e power minus s. So, replacing the value of 1 by e to the power x minus 1, I will obtain like this. Mellin function of 1 by e power x minus 1. This equals, I can write down summation n equals 1 to infinity 0 to infinity s minus 1 into e power minus n x dx, and this is nothing but again summation n equals 1 to infinity will be there. Value of this integral is nothing but gamma s by n to the power s. I am not going to again that how I am coming to this, because these are the standard integration results, and so I am directly writing this equals summation n equals 1 to infinity into gamma s by n to the power s, and this equals actually I can write down gamma s into zeta s, gamma s into zeta s, this we call as zeta s, where zeta s is equals to summation n equals 1 to infinity 1 by n to the power s. This is actually this zeta s, we call it as a famous Riemann Riemann zeta function. So, basically this is famous Riemann zeta function. So, zeta s equals summation n equals 1 to infinity 1 by n to the power s, and this is Riemann zeta function. Therefore, Mellin transform of 1 by e to the power x minus 1 is gamma s into zeta s, where zeta s is nothing but the famous Riemann zeta function. So, if I see over here, your f x is this thing and e power x you are getting as this. So, that Mellin function of 1 by e power x minus 1 equals 0 to infinity x to the power s minus 1 1 by e power x minus 1 dx. Now, we are using this series that 1 by 1 minus e power minus x equals summation n equals 0 to infinity e power minus n x, and this we can rewrite as n equals 1 to infinity. This 1 will be cancelled over there. So, that summation n equals 1 to infinity e power minus n x is equals to 1 by e power x minus 1. Simply by adding 1 on this side, subtracting, I will obtain this. So, once I am getting this 1 by e power x minus 1 is summation n equals 1 to infinity e power minus n x. I can replace 1 by e power x minus 1 by this series. So, that Mellin function of 1 by e power x minus 1 I can write down this integral, which is nothing but your summation n equals infinity value of the integral 0 to infinity x to the power s minus 1 e power minus n x dx is nothing but gamma s by n to the power s, and this equals I can write down gamma s into zeta s, where zeta s is equals to n equals 1 to infinity 1 by n to the power s, and real part of s is greater than 1, because as we have told s is a complex number. So, this zeta function zeta s is nothing but the famous Riemann zeta function. Our next problem is say f x equals 1 by x to the power 1 by 1 plus x to the power n. To solve this problem, your function is 1 by 1 plus x whole to the power n. So, that Mellin transform of 1 by 1 plus x whole to the power n, this is equals to 0 to infinity x to the power s minus 1, 1 plus x to the power minus n into dx. Like the earlier problem, if I substitute, you put x equals v by 1 minus v. So, that your v will be equals to x by 1 plus x and 1 minus v will be equals to 1 by 1 plus x. This I have told you earlier also. So, that 1 by 1 plus x can be replaced by 1 minus v. So, that it becomes again the limit will be from 0 to 1. I explained earlier, for x equals 0 your v is 0 and for x equals infinity your v is 1. So, that it is equals to v to the power s minus 1 into this is 1 by 1 plus x whole to the power n, and 1 plus x whole to the power n means 1 plus v to the power n. So, this becomes 1 minus v to the power, I can write down n minus s minus 1 into dv. Your v I am dv I am calculating from here, and from there by using this thing we are getting this. So, this integral by this substitution x equals v by 1 minus v, I am getting this. Again this is nothing but in the form of a beta function, beta s comma n minus s, because v to the power m minus 1, sorry, this is 1 minus v. V to the power s minus 1 into 1 minus v to the power n minus 1 into ds, which is nothing but beta s beta n minus s, and this equals, if you wish, you can write down gamma s gamma n minus s by gamma n. Your s will be replaced over there. So, the Mellin function of 1 by 1 plus x whole to the power n is equals to beta s comma n minus s, and in terms of gamma function you can write it as gamma n minus s divided by gamma n. So, if I see here, your f x is 1 by 1 plus x whole to the power n. So, that Mellin function of 1 by 1 plus x whole to the power n, you can write down 0 to infinity x to the power s minus 1 plus 1 minus x whole to the power minus n dx. Let us put x equals v minus 1 by b as I have shown in the working. So, this will be changed as 0 to 1 v to the power s minus 1, 1 minus v to the power n minus s minus 1 into dv. So, this is nothing but beta s comma n minus s, m is s minus 1, m is s and n is your n minus s, and in terms of gamma function I can write it as gamma s gamma n minus s by gamma n. Now, we want to find out the Mellin transform of sin k x and cos k x, say. From the first problem, if you remember, we have done this thing, Mellin transform of e power minus I k x. Mellin transform of e power minus I k x, this is equals, from the problem 1 already we have done, gamma s by I k whole to the power s. This equals, you can write down gamma s by k to the power s, and your I to the power minus s is going over there, which in terms of cos and sin you can write down, that is cos s pi by 2 minus I sin s pi by 2. This I can obtain this thing I to the power minus s, which if I take it over there, and I can write it like this. So, from here if I take the real and imaginary part, because e power minus I k x, I can write it cos k x and sin k x format. So, if I equate here, if I separate if I separate real and imaginary part, what I will obtain from here? I can obtain Mellin transform of cos of k x equals k to the power minus s, it will go up gamma s into cos of s pi by 2. And similarly, Mellin function of sin k x, this can be written as k to the power minus s gamma s into sin of s pi by 2. This I may denote it as A and B. So, effectively you see, by using the Mellin transform of e power minus I k x, I am finding this, then simply equating the real and imaginary part, I can tell the Mellin transform of cos k x as k to the power minus s gamma s cos s pi by 2, and Mellin transform of sin k s as k to the power minus s gamma s into sin s pi by 2. And I will just show you the application of this. Using this Mellin transform, you can find out Fourier cosine transform and Fourier sine transform of the functions also, of this function itself. So, that I will show you. So, Mellin transform of sin k x, we know it using the equation 1, using the problem 1. Mellin transform of e power minus I k x is gamma s by I k whole to the power x, which you can write down as gamma s by k to the power s, and I power minus s can be write down cos, and this I can write it as cos s pi by 2 minus I sin s pi by 2. E power again I can change it in the form of cos and sin, and if I equate the real and imaginary part, I will obtain Mellin function of cos k x as k power minus s gamma s by cos s pi by 2, whereas Mellin transform of sin k x equals k to the power minus s gamma s sin s pi by 2. Now, I will see, using the Mellin transform of cos k x, can I find out the Fourier transform of this. To do this one, 0 to infinity x to the power s minus 1 cos k x dx is nothing but the, we know it, that this is your Mellin transform of cos k x, whose value we have just now evaluated, gamma s by k to the power s into cos of s pi by 2. This already evaluated. This is nothing but the Mellin transform of cos k x, already we have done it, 0 to infinity x to the power s minus 1, this thing, and Fourier cosine transform of x to the power s minus 1. What is this? From definition, it is root over 2 by pi 0 to infinity x to the power s minus 1 into cos of k x dx, f x into cos of k x dx. From the definition of Fourier cosine transform, we can write down Fourier cosine transform of x to the power s minus 1 equals root over 2 by pi 0 to infinity x to the power s minus 1 cos k x dx. And this integral is nothing but the Mellin transform of cos k x, whose value already we know. So, that root over 2 by pi into gamma s by k to the power s into cos of s pi by 2. So, using the definition of Mellin transform of cos k x, I can find out the Fourier cosine transform of x to the power s minus 1, and similarly you can prove that Fourier sine transform of x to the power s minus 1 will be equals to root over 2 by pi gamma s by k to the power s into sine of s pi by 2. On the same way, using the Mellin transform of sin k x, we can prove that Fourier sine transform of x to the power s minus 1 equals root over 2 by pi gamma s by k to the power s into sine s pi by 2. So, we have done up to this, we evaluated this separating the real and imaginary part, Mellin transform of cos kx and sin kx. Now, 0 to infinity, Mellin transform of cos kx is 0 to infinity x to the power s minus 1 cos kx dx, whose value we have evaluated. Now, Fourier cosine transform of x to the power s minus 1 is nothing but root over 2 by pi 0 to infinity x to the power s minus 1 cos kx. If I evaluate the value, I will obtain Fourier cosine transform of x to the power s minus 1 is root over 2 by pi gamma s by k to the power s into cos of s pi by 2. And on the same way, I can show that Fourier sine transform of x to the power s minus 1 will be equals to root over 2 by pi gamma s by k to the power s into sine s pi by